We're told that sugar is the primary driver of glycation, but that's not the full picture, and I'll explain why in today's episode of the Energy Balance Podcast, a podcast where we explore health and nutrition from the bioenergetic view and teach you how to maximize your cellular energy to maximize your health. In today's episode, I'll be going over why glucose and fructose are not the primary drivers of age formation. I'll also discuss whether blood sugar spikes cause glycation, how fats and ketones can cause glycation, what's really responsible for glycation that occurs in type 2 diabetes, and also whether fructose actually causes more glycation than glucose. As always, to check out these studies, articles, and anything else that I reference throughout today's episode, you can head over to jfeldmanwellness.com/podcast. And with that, let's jump right in. All right, so in the alternative health sphere, we have this general idea that sugar causes glycation, which then causes aging. It literally ages your cells, it ages your body, and causes you to age and degenerate. And if you eat more carbohydrates, which all break down into sugar, then you'll have higher blood sugar levels and higher sugar availability in general. You'll have more blood sugar spikes, and this will cause more glycation. And then this is going to damage your blood vessels. It's going to damage all of your organs. And then it's going to age you. It's going to cause degenerative processes and cause, chronic health issues. And you'll frequently hear things like that glucose and fructose spikes will cause glycation. So avoid high carb diets, avoid eating frequently as well. Having fewer meals is better because you have fewer of these spikes. We'll also hear that in general, low carb diets will lead to lower blood sugar. So then they'll lead to lower glycation. So a low carb diet is better from a glycation standpoint. We'll hear that fructose is more glycating than glucose. Sometimes people will say as much as 10 times more glycating than glucose. So we should be avoiding fructose at all costs. Any sources of fructose, whether it's high fructose corn syrup in soda or it's fructose that's found in fruits. And then we'll also just hear in general that we want to cut out all sugar sources to prevent glycation. Again, with the idea that sugar sources also includes just any carbohydrate that, will eventually break down into sugars, into glucose and fructose or galactose. But in any case, this is the kind of general lay of the land that we're given, but we'll be talking today about why this is not the case. And this will be a two-part series here talking about glycation because there's a lot to dig into, a lot of misconceptions and misunderstandings when it comes to glycation. And so we want to make sure that we dispel all of that and dig into the details here. And we'll start with just the question of what is glycation, what's going on here, and then we'll talk a bit about what causes it and what the process looks like. As a starting place, the kind of strict definition of glycation is basically the chemical modification of an amino acid by a sugar. And this is an interaction that then damages the amino acid. And typically that amino acid can be a part of a larger protein. And most of your body is made up of protein. So this can be, a sugar interacting with some sort of protein structure that then damages it. And as this degradation occurs, it eventually leads to more advanced glycation products. There are early, intermediate, and advanced glycation products. And so as this process goes on, you tend to progress toward the advanced glycation end products. And so that's kind of the very strict definition, but it's also worth mentioning that glycation products, everything up to the advanced glycation products, are also produced without any sugar at all, from fats through lipid peroxidation. We'll talk about that. Also through ketones and through amino acids. So with that, the broader definition of glycation generally includes these things and basically involves any process that creates damaged amino acids that are then called glycation products. So that's really what we're talking about here is damage to amino acids, damage to proteins. And this can happen through a number of different mechanisms and from a number of different substrates, a number of different kind of precursors. And so the general progression that we have when it comes to glycation looks like this. So we start with the early glycated products, then we have the intermediate glycated products, and then the advanced glycated products or the advanced glycation end products. And what we're seeing here is the kind of standard diagram that you'll see that starts with a sugar. Normally this is going to be glucose. We'll talk about this with fructose as well. And then it goes through its progression here into a Schiff base and then an amidori product, which then can become an advanced glycation end product. So that kind of top part here is normally, in a lot of cases, especially in the low carb sphere, that's kind of the full picture that we're given. But there's a lot more to this picture that we want to discuss. And you can see a little bit at the bottom where you can see that intermediates from glycolysis, glycolytic intermediates, can also become advanced glycation end products. On the bottom middle here, they show that lipid peroxidation can also cause advanced glycation end products. And we'll be talking about those things in detail. But this is just our kind of general framework. And then here are some examples that we have of advanced glycation end products. Some of these actually aren't advanced. Some of these are like intermediate glycation end products. You can see hemoglobin A1C, that's one that we measure in the blood. And so we'll definitely be talking about that. But a number of these other ones here, CML is going to be one that comes up quite a bit. And you can see the acronyms here for a number of different advanced glycation end products. CEL is another very common one that we'll be discussing as well. It's one that's looked at in some studies. It's not important to know the details here, as far as these different ages, but this is basically the product of glycation if it progresses on without something kind of preventing it or causing it to go in the other direction, which we'll talk about here in a moment. But it is worth noting that advanced glycation end products are not a good thing. They do have negative effects. They are generally inflammatory. They're generally damaging, and they actually damage the proteins, so that renders them ineffective, unable to, exert the processes that they need to for function. And so generally, we don't want to see increased ages. And another thing that they do is they activate what's called the RAGE, the receptor for advanced glycation end products, RAGE. And that then has a number of downstream effects. And so we can see that here, where we have the ages, and when they interact with RAGE, you then see the activation of these different inflammatory pathways. In this case, we can see that they increase NF-kappa beta, which is an inflammatory cytokine. We can see that it leads to all of these pro-inflammatory processes, and this can contribute to endothelial damage, kidney cell damage, liver disease, obesity, and on from there. It's generally not a good thing in terms of its kind of causative effects, where it does drive inflammation and damage, and also it's generally happening in the context of chronic health conditions and a highly inflammatory state, and we'll talk about that too. But so that's our broad picture in terms of the progression of glycation and also, what ages are and their kind of general effects. But it's worth talking about the details in terms of the sources of ages, because as I've alluded to, the general narrative we get is that glucose or fructose are glycating. Those are the main glycating agents, and they cause the production of these advanced glycation end products. And so we might see something like this. Again, this is similar to that diagram I was showing you earlier, where we're seeing the progression from glucose into the early, intermediate, and advanced glycation end products. And there's a feature here, another aspect of this that's important to mention, which is the timeline through which this happens. This is actually an extremely slow process, and we can see this here. It's a little bit blurry, so it's kind of hard to see, but they show that progression into the early glycation products, that takes days to weeks. So this is, again, a very slow process. You have to have a lot of time for this interaction between the glucose and amino acids in this case. And then in the process of going from early glycation products to advanced glycation end products, we're talking about a time frame of months to years. So it's an extremely slow physiological process. And as we'll talk about, this isn't a permanent process until it reaches the advanced stage. So when you have the early and intermediate glycation products, these are reversible pathways. And so we can actually detoxify these early and intermediate glycation products. And so with how slow this happens, this is not particularly concerning relative to other things that are far more glycating, but this general glycation process of, interaction between glucose and amino acid like this is a very, very slow process. And it requires that you have this free sugar available and interacting with an amino acid for a pretty extended period of time. And again, during this period of time, there's a lot of time for detoxification to occur. And it's important to note, if we look back at the first image here, that the conversion from glucose to a Schiff base, that's reversible. You can go back from a Schiff base back to glucose. And the conversion from a Schiff base to an Amadori product is also reversible. So all the way up to these intermediate glycation end products, you can go backward. And we'll talk about what will detoxify and also what will lead to the regression back toward glucose and basically prevent this from continuing on until it becomes the advanced glycation end products. Once that happens, it is permanent in that you can't go backward to the intermediate glycation products, but we can still clear out those advanced glycation end products. So we can still clear out the ages. And so we'll talk about that process as well and what affects it. So that's the glucose side. We'll talk a bit more about fructose later on. It's a very parallel process as far as what we saw here with glucose. But despite the name glycation, which does imply that this is glucose driven, it's not only driven by sugars. It's not only driven by glucose and fructose, and it can also be driven by fatty acids and ketones, even in the complete absence of glucose or fructose. And so that's touched on here in this diagram, where again, we see the early glycation products, the Schiff-based amidori products from glucose. We just talked through that process and how those can be converted over to the right into the advanced glycation end products. But you also see on the bottom left, we have these oxoaldehydes. And these are intermediate glycation products. They're also called dicarbonyls or alpha dicarbonyls. We'll be talking a bit about these because there's a number of different substrates that can be converted into these. And these are really highly reactive. We'll talk about the details because it's crucial to get into the details with these. But these are really major drivers of the advanced glycation end products, many, many times more glycating than something like glucose. And as you can see in the bottom left here, lipids, amino acids, and ketone bodies can all be precursors to these alpha oxoaldehydes, these dicarbonyls. Again, we see here glyoxyl, methylglyoxyl, and glycoaldehyde. These are the three primary ones that you want to be aware of. And again, these can be produced, and we'll go through the pathways briefly. We'll just kind of go through an overview of them in terms of how lipids, amino acids, and ketones can become these and then can become advanced glycation end products. Again, entirely in the absence of sugar. And that's very important because that's not normally the narrative we're given. We're given the narrative that this is sugar-driven, this is glucose, this is fructose. And so we have a good example here when it comes to looking at the age content, the advanced glycation end product in foods. And this is not something that we generally want to concern ourselves with too much. The absorption of these ages is pretty low, and there's very high levels of excretion. So I would say generally we don't have to be concerned about the amount of ages in food. But looking at the age content of food illustrates how much advanced glycation end products we can have, or how much glycation we can have, even if we were eating a very low carbohydrate diet, even without much, if any, carbohydrates available. And so we'll look at this table here. This is from a study titled Advanced Glycation End Products, Ages, Formation, Chemistry, Classification, Receptors, and Diseases Related to Ages. And we can take a look at this table, and we're looking at the age content per 100 grams. And looking at these numbers, it's pretty surprising because what you might expect is the sugar-containing foods will have the highest amount of ages, apples, they show tomatoes, they show honey, and bread, which, of course, that's a starch, but, that starch will break down into glucose. And the amount of ages in these things is very small. Apples, even when they're baked, fresh apple, it shows 13. But then with a baked apple, you would think with, introducing heat into these free sugars, you would see a lot of age formation. And you don't, only a level of 43, honey at 7. And then when we compare that to some of the fat and carb sources, it's pretty surprising. So with butter, we see a level of 26,000. And again, I'm not saying that that's a bad thing. As I was mentioning, I'm not necessarily concerned about dietary age content here. And I think butter is generally a health food, but it definitely says something when, someone is trying to eat let's say a butter-based diet, a high-fat diet, a low-carb diet to avoid ages. Well, obviously butter and the components in there are not immune to ages. We see that when we look at chicken as well. So boiled chicken has a level of 957. Chicken breast that's raw, level is 769. Beef that's raw, 707. Obviously, when it gets into the cooked meats here, cooked turkey and bacon's at 91,000. So again, this doesn't mean that we shouldn't be eating, beef or chicken breast or something. That's not at all what I'm saying, but it definitely says something about this idea that, if it's as simple as the sugar leads to age formation, age production, then, we wouldn't be seeing these sorts of values, these massive orders of magnitude differences between the age content of these different foods. Again, not something to be particularly concerned about from the dietary side. But as we'll continue to discuss as we go through some of the physiology here and then talk about the implication of different diets and, what will affect these different pathways and how we can actually minimize glycation. One thing that we're definitely getting at is that carbohydrates and sugars are not the culprits behind glycation, so you don't need to avoid them for that reason. But that doesn't mean that all carbohydrates are created equal when it comes to our metabolic health, and the same goes for fats and proteins as well. They're not all created equal. And that's why I've created the Energy Balance Food Guide to help you determine exactly what to eat to optimally support your metabolism and help you lose weight, improve your digestion, get amazing sleep, boost your energy, and so much more. The Energy Balance Food Guide is a one-page infographic that organizes foods on a spectrum based on how effectively they support your metabolism, and it also has a separate spectrum that adjusts this scale for you in the case that you're dealing with various digestive issues. The Food Guide makes it extremely easy to get started with a bioenergetic approach to optimizing your health. So head over to jfeldmanwellness.com/guide to download your free Energy Balance Food Guide. With that, let's talk a bit about those dicarbonyls. We talked about these a little bit earlier, glyoxal, methylglyoxal, and these are really the primary drivers of age formation. So it's important to spend some time talking about these and what their sources are and how we can minimize their production. And again, whether it all just comes back to sugar. And I do want to mention here, Chris Masterjohn has a really good article on this titled, "Where Do Most Ages Come From? O Glycation, How Thy Name Hast Deceived Me." It's a great title for the article as well. And so I just wanted to mention that here because he discusses a lot in terms of these dicarbonyls. And so a lot of the information here is building upon his article. So I did just want to mention that as one that I would highly recommend checking out. But with that in mind, let's talk about what these dicarbonyls are, how they're produced, what they do, and why they're so concerning. The first to mention here, so basically there are 3 dicarbonyls that are generally considered to be the glycating dicarbonyls, the ones that are going to create the advanced glycation end products, and they themselves are considered intermediate glycation products. And these are methylglyoxal, glyoxal, and 3-deoxyglucosone. And again, it's not, the names aren't particularly important. I wouldn't concern myself too much with those, but we see those here, and we can also see their different sources here. So we talked about the Maillard reaction. This is the, glucose into the Schiff bases, the amidoid products. And we talked about those as a potential source of these and ages, but there are a handful of other factors as well, like lipid peroxidation, glycolysis, and we'll talk about some other ones here too. They mentioned the polyol pathway. There's a number of different pathways that can lead in here, and we're going to talk about them in a little bit more detail, not a ton, but it's really important to talk about these dicarbonyls because they are the primary precursors to the ages. And we can see some of these ages here that we saw in that chart earlier. And the reason for this is because dicarbonyls are 20,000 times as reactive as glucose. And so if someone is describing that glucose is this compound to be very fearful of because it's so glycating, well, you definitely want to keep that in context when we're talking about compounds here that are 20,000 times as reactive and that we want to be much more aware of and aware of what actually increases their formation, which does happen to include other substrates like fats and ketones, as we'll discuss. But I'm just going to share this quote here first, describing how glycating they are. And so this is from a study titled "Dicarbonyl Intermediates in the Maillard Reaction." And they state, "The formation of alpha-oxoaldehydes," this is the dicarbonyls that we're talking about here, "enhances and redirects glycating activity in the Maillard reaction, since alpha-oxoaldehydes are up to 20,000-fold more reactive than glucose in glycation processes and are predominantly arginine-directed glycating agents." So just pointing out, just highlighting how concerning these dicarbonyls are when it comes to glycation. And one of the main ones here that we've mentioned a couple times is methylglyoxal. This is one of the most common ones that's measured in different studies and that's looked at in general. So we're going to talk a little bit about methylglyoxal and what kinds of things form it and what the contexts are for methylglyoxal. We're going to start here by looking at one of the primary sources of methylglyoxal, which is the triose phosphates. So again, I know this sounds a little complicated, but as we go through the physiology here, we'll get into more application as well. And also, if I'll try to simplify it here, but some of the big names and everything sound a little bit more technical than they are. So what we're talking about here is when we have glucose on the left and we start to run through glycolysis, which is the process of converting glucose to energy, we produce these different steps along the way, these different intermediates, and a few of them are what are called triose phosphates. And one of these is glyceraldehyde 3-phosphate, and then the other one is dihydroxyacetone phosphate, that's the DHAP. So those two are just produced anytime you're converting glucose into energy. And we'll talk about the context of this, but essentially, if there's a buildup of these intermediates because glucose metabolism is blocked, you'll see them build up. And when that happens, or just if there's an excessive amount, we'll talk about those contexts, you'll see a conversion into methylglyoxal. Both of these can be precursors to methylglyoxal. And again, methylglyoxal being one of these dicarbonyls that's very, very glycating, one of the main glycating agents. And we can see if we follow that methylglyoxal arrow to the right, we can see that it produces the ages. Now, we can also see in this diagram another source of methylglyoxal, which is the polyunsaturated fats that become lipid peroxides. So this is something we talk about all the time. We talk about the negative effects of PUFA, and that's because they can get damaged. They're inefficient for energy production, and they produce these lipid peroxides. And one of the negative effects of these lipid peroxides is they can directly be converted into methylglyoxal, which again can then become AGEs. We'll also talk about some ways that lipid peroxides can also just directly become AGEs or advanced lipoxidation end products. We'll talk about those in a bit. And you can kind of see that on the right of this diagram here. But the important point being that, these are two different sources. We have these triose phosphates coming, in this case, from glucose. They could also come from fructose, or they could come from gluconeogenesis, or they could come from other sources. We'll get into all that. But then also we have the polyunsaturated fats on the right that can produce this methylglyoxal. And you can also see on the bottom here that methylglyoxal can be converted or basically detoxified and converted into D-lactate. This is via glyoxylase and utilizes glutathione. And this is actually something that we'll be talking about more in part 2. But those are a couple sources here of methylglyoxal. A couple of others include one, the amino acid threonine, and then acetone. And so we see that described here where they're showing the different sources of methylglyoxal, glycolysis, and lipid peroxidation that we discussed, but also threonine, which is an amino acid, and acetone, which will kind of show that pathway in a moment. But these are both also potential precursors to methylglyoxal. And then we're going to see this, we see this pathway here when it comes to acetone. And, this is pretty important because acetone is one of the main ketones that's produced, and it's a direct precursor to methylglyoxal. And then from this pathway, it can actually be converted into glucose in the process of gluconeogenesis. So one of acetone's main roles, so if someone's on a ketogenic diet and they're producing a lot of acetone, one of the main things that happens with that acetone is it's used for gluconeogenesis. It gets converted into glucose. In that process, methylglyoxal has to be produced. And so you end up with these increased levels of methylglyoxal and a direct increase in AGEs, and we'll be talking about this a bit more later on, but it's pretty important to note here when we just see this pathway drawn out here in this diagram. And then with that, something else that we want to be aware of on a low-carb diet or a diet when we're eating excessive amounts of protein and just a lack of carbs, or especially on a ketogenic diet as well, is gluconeogenesis. And this is also something that comes into play with insulin resistance and diabetes. And so we see this here where if we look at A on the left, we saw, those triose phosphates, which are in the middle there. Glucose can be a source of those, but another source of those is gluconeogenesis, which we see that pathway all the way on the left, the pink and yellow there, where anytime we're producing glucose from any substrate, we will see these triose phosphates that have to be produced along the way, and those are also precursors to methylglyoxal. So if you think that you're avoiding any of these pathways by avoiding carbohydrates, this obviously is not the case, and we're still going through all of these intermediates that are the precursors to methylglyoxal and to AGEs. And then we see on the right here just a few of those other sources. We see acetone on the bottom right, and acetoacetate is a precursor there, and the Maillard reaction and threonine that we had talked about earlier. And so these are our main sources of methylglyoxal, which is one of the main drivers of age formation. Obviously, what we're seeing here is this is not just a sugar problem. There's a bunch of different substrates that can lead to an increase in methylglyoxal, and we'll talk about the context under which this happens and how to prevent it from happening. But, it's definitely clear here that this is not just a sugar-driven process. And this study goes along with this as well and basically shows us how in healthy conditions, when we're utilizing glucose as a fuel, when we're utilizing carbohydrates as a fuel, methylglyoxal production is actually pretty minimal. But of course, when we're not under healthy conditions, that's when things can change. But we'll take a look at the quote from this study titled "Methylglyoxal-Induced Dicarbonyl Stress in Aging and Disease, First Steps Toward Glyoxylase-1-Based Treatments." And they state, methylglyoxal is formed mainly from the spontaneous trace level 0.05 to 0.1% flux degradation of triose phosphates. This increases with increased triose phosphate concentration in anaerobic glycolysis. So just to pause here, under normal conditions, we're seeing a very, very tiny amount of methylglyoxal production. But they mentioned that this increases in anaerobic glycolysis. This is something that we see going on when glucose metabolism is inhibited, when there's excess fatty acid metabolism going on. This is something that we've talked about in prior episodes on insulin resistance. I'll link to those in the show notes. Moving along here, they state abnormal physiological metabolism leading to increased triose phosphate concentrations are increased glucose metabolism and hyperglycemia associated with diabetes. This isn't really increased glucose metabolism per se. It's increased glycolysis or anaerobic glycolysis, as they mentioned, with inhibited glucose oxidation. So basically you have kind of like a broken glucose metabolism. And this is a case where you'll see increased triose phosphates, which then will increase methylglyoxal. They go on to state, Another situation which is impaired disposal of glyceraldehyde 3-phosphate by the decreased activity of the reductive pentose phosphate pathway and increased dependence on anaerobic glycolysis and related increased metabolic flux in hypoxia, which is the Pasteur effect. It may also arise from other metabolic pathways where triose are intermediates, including gluconeogenesis, glyceroneogenesis, and rare triose isomerase deficiency. So that last part is important here as well. When we're seeing increased gluconeogenesis, these intermediates will also be elevated, and that's going to happen in situations like insulin resistance and type 2 diabetes due to high stress hormones, and also under the case of low-carb diets, we see increased gluconeogenesis as well. So that's just a little bit of context regarding methylglyoxal production under normal states versus these impaired metabolic states. And that brings us to one of the other main sources here that we want to talk about, which is the peroxidized fats, especially polyunsaturated fats, since those are the ones that are particularly susceptible to damage and to peroxidation. And we see that in this diagram here. We talked about this one earlier, where we can see that the polyunsaturated fats that become the lipid peroxides, if we follow down to the right, we can see the production of malondialdehyde and 4-hydroxynonenal. That's also 4-HNE. There's some other ones in here. There's some other compounds that fall in this category, like acrolein as well. These are aldehydes that are produced from lipid peroxidation. They're implicated in basically every chronic health condition you can think of, and they're also precursors here to the advanced glycation end products and also to methylglyoxal. They can also be converted to these dicarbonyls, which they aren't actually showing that direct arrow here, but that is also a potential pathway. And so this is extremely important. The polyunsaturated fats are huge drivers of advanced glycation end products that we want to be aware of. And this is especially notable when you have figures, some of the figures who are most prominently fear-mongering about sugars because of glycation, figures like Ken Berry, who have stated in the past that naturally occurring omega-6s aren't harmful. Yet what we see here is that they're actually direct precursors to advanced glycation end products, and they're actually far more glycating than sugars like glucose. And we see that here. This is a study looking at omega-6s and their propensity toward forming advanced glycation end products. This is a study titled The Advanced Glycation End Product, Nepsilon carboxymethylysine is a product of both lipid peroxidation and glycoxidation reactions. And they state, CML was also formed in a time-dependent manner in RNase incubated under aerobic conditions in phosphate buffer containing arachidonate or linoleate. So linoleate, that's linoleic acid. That's the omega-6 fat that's really common in the high omega-6 foods. They state only trace amounts of CML were formed from oleate. After 6 days of incubation, the yield of CML and RNase from arachidonate was about 0.7 millimoles per mole of lysine, compared with only 0.03 millimoles per mole of lysine for protein incubated under the same conditions with glucose. Glyoxal, a known precursor of CML, was also formed during incubation of RNase with arachidonate. So arachidonic acid is a downstream fatty acid that gets produced from linoleic acid. It's produced from the omega-6s. And what we see here is a 23 times difference between arachidonic acid and glucose in terms of forming advanced glycation end products. And they did actually look at linoleic acid as well, and they found it to be about 10 times greater than the glucose formation of advanced glycation end products. The amount was about 0.35 millimoles per mole of lysine. So what they found was that the omega-6s were 10 times more glycating than glucose. And it's worth noting, this is only considering the advanced glycation product CML that's produced from the omega-6s. It's not considering the ALEs, the advanced lipoxidation end products. And if we account for those as well, then we would really see that the polyunsaturated fats and especially omega-6s are far more concerning from this standpoint. And the ALEs, this is basically an alternative way. It's independent generally from the advanced glycation end products. They fall under the same umbrella. They have the same effects. They actually do the same things in terms of damaging the proteins, accumulating with time in these chronic health conditions and degenerated states. They activate the same RAGE receptor, the receptor for advanced glycation end products. It's also activated by these ALEs, and it activates the same inflammatory pathways. So they function, basically the same, but they're just being driven only from fats and from lipid peroxidation. Basically what can happen, and we can see this here in this diagram, is that these aldehydes that are produced from the lipid peroxidation, we see them here as reactive carbonyl species. This is the 4-HNE, MGA, acrolein. These can be converted into the dicarbonyls like methylglyoxal and then can form, the AGEs, or as we're seeing here, they can directly interact with the amino acids. So without needing to convert to methylglyoxal and then convert to AGEs, these aldehydes can directly interact with amino acids and form what are called ALEs, these advanced lipoxidation end products, which again are just as harmful as the AGEs. And we see this here in this other diagram where we see they're highlighting specifically the PUFA, the lipids, and all of the products that they produce here, these reactive carbonyls, and then how they can end up creating AGEs and ALEs. So it's really a huge part of the picture here that isn't often talked about is the polyunsaturated fats and how much of a driver they are of AGEs and ALEs. And when it comes to this broader conversation of glycation, they're a really important player. So we have this general landscape, which is basically that in an impaired metabolic state, we'll see increased precursors to advanced glycation end products. We'll see increased production of these advanced glycation end products. This comes from all sorts of sources, whether it's sugars, fatty acids, or ketones. And avoiding any of these on their own is not going to be a solution, right? That's not actually going to make a difference when it comes to age formation. We really need to be looking at the metabolic state. But it's worth addressing, I think more specifically, the concerns regarding blood sugar and glycation, because again, we're constantly bombarded with this idea that a glucose or a fructose spike after eating carbohydrates will be causing glycation, damaging blood vessels, and causing degeneration. And so let's dig into that question a little bit of whether high blood sugar does actually cause glycation and advanced glycation end products. The first thing that's really worth noting here is that what's going on in the blood in terms of glycation is far less important because most of the formation of glycation products is occurring inside the tissues. It's not going on in the blood. So these short-term fluctuations of sugars or fatty acids in the blood are not as concerning versus the metabolic state of the tissues. And this study describes that here. This is a study titled Quantitative Screening of Advanced Glycation End Products and Cellular and Extracellular Proteins by Tandem Mass Spectrometry. And they state quantitative screening showed high levels of advanced glycation end products and cellular protein and moderate levels in protein of blood plasma. Low levels of free advanced glycation end products were found in the blood plasma, and levels were 10 to 100-fold higher in the urine. This is when they're being excreted. We showed for the first time that cellular proteins are more highly glycated than extracellular proteins. So, and they go through this in the study with different tables, but what they're essentially finding is that there was relatively low amounts of the glycation products in the blood and outside of the cells. Most of this is happening inside the cells, inside the tissues. And so what we really want to do is focus on what causes that, what affects those processes. One piece I want to touch on here that I think is important because there's a bit of conflation here is what goes on in type 2 diabetes. Because we know in type 2 diabetes that there's high levels of blood sugar. And we also know in type 2 diabetes that there's a large amount of glycation that goes on. But what we're seeing in this state when people are connecting those two together and saying, okay, well, blood sugar is causing the glycation is basically a huge conflation of these two factors. And it's the same thing that happens when we see high blood sugar and insulin resistance, where the blood sugar is not causing the insulin resistance. It's the effect of the insulin resistance. It's the part of the body's response to the insulin resistance. It's not actually driving it. And same goes for insulin. Again, we've talked about this in those previous episodes on insulin resistance. But so we're seeing a similar situation here where the glycation that's going on here in type 2 diabetes is definitely related to the blood sugar, but it's not directly caused by it. It's actually a situation where it's being driven by the underlying metabolic state that's also causing the high blood sugar. And with that, we want to remember that the advanced glycation end products from sugars themselves is extremely slow, right? We're talking days, weeks, months, years. And so this is really not the primary source of glycation that we want to be concerned with. Rather, we do actually want to be concerned about glycation going on in the state, but it's more so due to the poor glucose metabolism that's going on and the impaired metabolic state that leads to a low NAD plus to NADH ratio, as well as the increased lipid metabolism and the increased gluconeogenesis. And that is what leads to the state of increased glycation. Because in this situation, we kind of touched on this earlier, we have a buildup of the glycolytic intermediates, those triose phosphates that we talked about, where basically the glucose isn't able to be completely metabolized and converted to ATP. It gets stuck, and you have this buildup of intermediates. And they talk a bit about this in this study, which is titled Prevention of Incipient Diabetic Nephropathy by High-Dose Thiamine and Benfotiamine. And they state, supporting studies of mesangial and endothelial cells in hyperglycemic culture have exemplified the key features of biochemical dysfunction in hyperglycemia. The accumulation of triose phosphates, increased de novo synthesis of diacylglycerol, and activation of protein kinase C-beta, oxidative stress linked to mitochondrial dysfunction, sustained by high glycerophosphate shuttle activity, concomitant activation of the hexosamine pathway, and the accumulation of methylglyoxal with increased formation of AGEs, increased concentrations of triose phosphate glycolytic intermediates, glyceraldehyde 3-phosphate, and dihydroxyacetone phosphate is the trigger for these processes. So I know that was a lot there. The important part being, if we're kind of simplifying here, the buildup of those triose phosphates, which, we went over that diagram before, and we'll go back to a similar one, is really what's responsible and for the glycation in this state. And this is the result of mitochondrial dysfunction, basically impaired glucose metabolism. And this is important because what we're seeing here is even in the condition with the highest blood sugar levels, it's not the sugar in the blood that's responsible for the glycation. So this is really saying something when we're looking at a study like this. And so here's a diagram of showing the conversion of glucose to pyruvate. This is glycolysis. And we have those triose phosphates in the middle, the glyceraldehyde 3-phosphate and the dihydroxyacetone phosphate. These are the two that are precursors to methylglyoxal. And part of what's important here, you can see that the step after that converts the glyceraldehyde 3-phosphate to the 1,3-biphosphoglycerate. This is just, again, I know the names sound complicated, but we're just converting that glucose to energy. And this is one of those important steps. You can see in yellow, this requires NAD plus to be converted to NADH. And when we have a low NAD plus to NADH ratio, which happens in insulin resistance, metabolic syndrome, interference in mitochondrial function, we're going to have interference in this step. It's not going to function as well. And we'll see this buildup of these triose phosphates as a result. And so this is part of why when we talk about the NAD to NADH ratio, it's very important. This is not the only step that it's involved in, but this is something that we see happening in these states. We see this impaired glucose metabolism that leads to this buildup of triose phosphates, which lead to advanced glycation end products. And we see this diagram as well. This is specifically, we looked at the full one earlier. This is just a portion of that one that we looked at. And this is from a paper specifically talking about the increase in these triose phosphates and glycation in disease processes like type 2 diabetes. And what we see here is these different sources, the glucose that, again, is not going to be converted all the way down to pyruvate and then go through, mitochondrial respiration, it gets blocked. And then also the gluconeogenesis, which is actually increased in the case of insulin resistance due to chronically high stress hormones. Again, this is something we talked about in the insulin resistance series. But these are the sources of glycation in this situation. It's not just the glucose itself that's sitting in the blood. And the reason why this is so important to delineate is because it means that the moderate blood sugar bump that you get after eating even a high carb meal isn't actually responsible for glycation. It's not actually responsible for age formation. And we're seeing this in the most obvious situation of type 2 diabetes where there's massively high blood sugar levels. And again, what we are seeing is that if we can't use carbohydrates effectively, that's when we start to see glycation to be a concern. And it's not just because of the carbohydrates that we're consuming at that point. It has to do with oftentimes polyunsaturated fats that are implicated in that scenario. It has to do with gluconeogenesis going on, the stress hormones, a number of other things that are blocking mitochondrial respiration. And then that brings us to another point here that does go on in type 2 diabetes, which is that there's elevated oxidative stress in this situation, which causes the increased lipid peroxidation. We talked about this earlier because the lipid peroxides can be converted into the advanced glycation end products. But the other thing that it does is it reduces the clearance and detoxification of the intermediate glycation products and the advanced glycation products. So both sides of the equation are impacted in this impaired metabolic state. We see increased production and reduced clearance. But we'll discuss the clearance and detoxification side more in part 2. That brings us to one of the other important misconceptions to discuss here, and that has to do with fructose and glycation. So we're often told, again, from the people who tend to fearmonger regarding glycation and carbohydrates, we're told that fructose is more glycating than glucose, and if you're eating a lot of fructose-containing foods, whether it's table sugar or fruit or soda or candy or whatever it is, you're going to see an increase in fructose and therefore an increase in glycation from fructose, or what's sometimes called fructation. Let's talk about that a little bit. Again, it's one of those situations, like most, where there's a kernel of truth in there, but the application of it and the way that it's often described is really totally irrelevant. And it definitely does not mean that we need to be avoiding fructose in our diet. So what we'll look at here is a graphic of what's called fructation. And so, we talked about the first pathway, pathway A, that's coming from glucose, and that conversion down from glucose into AGEs. Pathway B is the same thing coming from fructose. And so it follows that same path. There are some other pathways of age formation from fructose, but this is kind of the primary one. There's one called the Wolff pathway, and there are some others. But in any case, much like glucose, we have this kind of basic pathway for the production of AGEs from fructose, and this is through a process that's basically equivalent. It's called fructation. And so one thing that you might hear is that this fructation process, or the capacity for fructose to cause glycation, is far greater than with glucose. We'll often hear something along the lines of, fructose is 7 to 10 times more glycating than glucose. And there is an old study from around 1980 that does look at this. They basically looked at fructose versus glucose and the reactivity of each in vitro. So this wasn't looking at it, in a person who's consuming glucose or consuming fructose or anything like that, just looking at the reactivity between glucose and fructose. And in this case, they were looking at hemoglobin. And they did find that fructose's reactivity with hemoglobin was 7.5 times that of glucose in regard to forming Schiff bases. Remember, that's that first step here of the fructation. So it's suggesting that the fructose is about 7.5 times more glycating than fructose. And it's worth noting, as I was kind of alluding to, that this is only shown in vitro. And when it comes to the in vivo studies, they don't actually show this comparison. And honestly, there's not a lot of great research looking at age formation in vivo. It's just, I guess you could say, understudied. Comparing different diets and their impact on glycation and things like that is just not commonly done. There are studies looking at the impact of fructose on glycation in rodent models. We'll touch on that in a little bit and how relevant it is. But again, what a lot of these claims are based on when they're talking about fructose being 7 to 10 times more glycating than glucose is this in vitro study. And even if we were to assume that this in vitro data is 100% applicable to humans in vivo, to us in our kind of regular environment when we're eating a fructose-containing diet, there are still some important caveats here that really nullify any relevance of this finding. And the first is that fructose levels in the blood are about 200 times less than glucose at baseline. So if we're concerned about, let's call it 8 times, fructose is 8 times more glycating than glucose. Well, fructose levels in the blood at baseline are 200 times less than glucose. So that, wouldn't be concerning if we're not concerned about regular levels of glucose in a healthy metabolic state, we wouldn't be concerned about that with fructose. And when it comes to the consumption of fructose, even when consuming massive amounts of fructose, the levels in the blood still are many, many times lower than glucose. So we already talked about earlier why fructose or glucose in the blood is not a concern when it comes to AGEs, because that's not where most glycation is happening, and it's not just sitting there. But then on top of that, the levels in the blood, even if you're concerned about fructose being more glycating than glucose, the levels are so much less that it's not relevant. We'll look at some studies here that are describing that. And again, these are going to be looking at, a level of fructose consumption of like 75 grams all at once. That's, the equivalent of consuming a few sodas at once. This is not relevant to consuming a regular moderate or high carb diet from whole foods. So I will get into that here with this first study, which is titled Metabolic Aspects of Fructose Metabolism and Metabolic Disease. And here we just have a quote talking about fasting concentrations of glucose and fructose, where they state, whereas normal fasting glucose concentrations in peripheral blood are around 5 millimolar, fructose circulates at less than 0.02 millimolar in fasted conditions. So 0.02 millimolar fructose, we're looking at about 0.36 milligrams per deciliter. And if we're thinking, fasting glucose of 80 milligrams per deciliter, this is 222 times lower at baseline, at fasting. So much less that, again, even if fructose was 100 times more glycating than glucose, it would still be less concerning than fasting glucose levels of 80 milligrams per deciliter, which obviously, whether you're on a low-carb diet or high-carb diet, you're not going to see fasting glucose levels that far below 80, especially if you're insulin sensitive. So, in either case, it really wouldn't be relevant here. And then in this study, we'll look at what happens when you consume large amounts of fructose. and what it does to blood levels of fructose. So this is a study titled Effects of Several Simple Sugars on Serum Glucose and Serum Fructose Levels in Normal and Diabetic Subjects. Again, this is looking at people who are metabolically healthy and people who have type 2 diabetes and what happens to fructose in the blood when consuming large amounts of fructose. And they were using 75 grams. This is the amount of fructose that's in around 3.5 cans of soda. So huge amount of fructose. And so we see here in figure 3, the levels of fructose after consuming 75 grams. And then we also see the level of fructose after consuming 75 grams of sucrose and glucose. And so what we see after this massive intake of fructose is that the levels peaked at less than 7 milligrams per deciliter. So even if you're on a low carb or ketogenic diet and you're seeing a fasting blood glucose level of 80 milligrams per deciliter, which by the way, most of what I see on from people who have been on longer term low carb diets is that blood sugar level increases quite a bit, often above 100 milligrams per deciliter with time of all the stress. But that aside, the less than 7 milligrams per deciliter is still more than 10 times less than baseline levels of blood glucose. So even if fructose was 10 times more glycating than glucose in vivo in a human, it still would be less concerning here than just fasting blood glucose levels. So what this really points to is that fructose is not a concern when it comes to glycation in terms of blood levels, which is often what's being pointed to. And you would think, okay, well, it's someone who's dealing with metabolic issues, who's insulin resistant, who has type 2 diabetes, maybe those blood fructose levels go way high, just like the blood sugar levels do. That's not actually what was found here. So in figure 5, they show normal subjects versus diabetic subjects, and the increase in serum fructose between the two was barely any different. And you can see the peak is still below 7 milligrams per deciliter. So the fructose levels in the blood are really not concerning. This is even after consuming 75 grams of pure fructose, which, by the way, you would never get pure fructose in any foods. It's always paired with some amount of glucose, whether we're talking honey, fruit, table sugar, which is 50-50, high fructose corn syrup, which is 55% fructose, 45% glucose. So even in this case of 75 grams of pure fructose, which is essentially irrelevant to what a normal human would be consuming, even then the fructose levels in the blood are not high enough to a point where it would warrant any concern in terms of fructation. One of the next things that we often hear when it comes to this idea that fructose glycation or fructation is particularly harmful, and we're getting this kind of fear-mongering spiel, is that you can't measure fructation. So this could be happening in the background, and you can never know if fructation is actually going on. And so it's this secret, killer in the background that's going to slowly age you. And again, there's a negative truth in here, which is that when it comes to the typical blood markers that are measured, like hemoglobin A1C or fructosamine, these are looking at early glycation products. They're not looking at fructation products. So it's true that in typical markers, if you just look at A1C, it's not telling you about hemoglobin that gets fructated. It's just telling you about hemoglobin that's glycated. But so if we're going off of the in vitro studies, and we're going to assume that fructose is, let's say, 8 times more glycating than glucose, and this was looking at hemoglobin. So we already know the interaction between glucose and hemoglobin creating A1C. And now if we can assume the fructose and hemoglobin and the fructation that's caused there, since we already know the difference in reactivity and we know the amounts of each in the blood at baseline and even after consuming massive amounts of fructose, we can very easily infer how much fructation is going on. And it's very obvious based on the levels that we just went through that we would be getting less fructation from fructose than we would get glycation from glucose. And again, we know this based on the study that we just went through, looking at baseline levels, the first study, and then the second study looking at how the increase in fructose after consuming incredibly high amounts of fructose is still lower than fasting glucose levels. And even if we consider the difference in glycation between the two, the fructation would still be less than we would get from fasting glucose levels. So with that in mind, it's obvious that even though you're not actually able to measure in a standard blood test the fructated hemoglobin, it's not actually relevant, and it's going to be less, far, far less than the amount of glycation you would see even from fasting glucose levels. So with that in mind, it really nullifies any concerns here when it comes to fructation, but we're going to take a look at the study that also corroborates this. This is a study titled Hemoglobin Fructation Promotes Heme Degradation Through the Generation of Endogenous Reactive Oxygen Species, where they state, in spite of fructose higher reactivity, its contribution to extracellular glycation has been less noteworthy than glucose. This is mainly attributed to the low plasma concentration of fructose compared with glucose. So again, pointing out exactly what we're describing here, which is that when we're looking at blood levels, it's really irrelevant. And outside of blood levels, everything else is the same in terms of what we described so far when it comes to glucose, in terms of this much broader conversation where, when we're comparing glycation and fructation, it's true that fructation isn't quite as slow as glycation. That first step is about 8 times faster. But in general, fructose levels in the blood are so low that that's not relevant. When it comes to the tissues, again, in a normal metabolic state, fructose is not staying as fructose. You're not consuming fructose and then it just goes into all your tissues and just sits there as fructose and waits for days and weeks and months to undergo fructation. We're constantly highly metabolically active organisms. And so once we get fructose, a lot of things happen. And, we see this very clearly when it comes to fructose. And I've described this in a previous episode talking about Robert Lustig's fear-mongering regarding fructose. And so check out that podcast if you're interested for the details. But essentially, once we get fructose, it goes to the liver and it's immediately converted to other products. It's converted to glucose, it's converted to lactate, it's converted to glycogen, it's utilized as fuel and converted to energy, but it's not just sitting there as fructose. And so it's not really a concern from that standpoint. Now, of course, fructose is a fuel, just like glucose is. And so the inhibition of the metabolic usage of that fuel will cause age production because it'll increase the triose-phosphates, and that will increase the dicarbonyl production, and that'll increase advanced glycation end products. But again, this is an issue with the inhibition of the metabolic function and inhibition of mitochondrial function, not actually the fructose itself. Again, this would happen whether we're talking about fructose or glucose. And in this state, you also see it happening with fats and ketones as well. And you see it happening whether you're consuming the fuel or not, whether your body is producing the glucose through gluconeogenesis or you're consuming it, it's going to be a precursor there for the triose-phosphates. So all of that is, just as relevant to the fructose conversation. And then along with that, a general state of impaired metabolic function and oxidative stress is going to reduce the detoxification of glycation products and the clearance of the advanced glycation end products. This applies with the fructation products as well. So again, none of this implicates fructose as a concerning glycating agent, even in the context of it being 8 times higher reactivity than glucose when it comes to the fructation capacity with hemoglobin. Now, I do want to touch on one piece here, which is when it comes to looking at fructose in animal models. And this is a very parallel situation to something that we've talked about when it comes to fatty liver, when it comes to uric acid. With most of the research looking at the negative effects of fructose, it occurs in situations that are entirely irrelevant to a normal physiological state, situations that are entirely irrelevant to food and how food is available, because food never just has fructose on its own. It's always paired with glucose, among other things. And it's also in models and in types of experiments that are totally irrelevant to us as humans. And so it is true that in some studies looking at animal models with high fructose diets, there is an increase in advanced glycation end products. However, like the other research on fructose that points to these negative effects, there are some major flaws here. One is normally there are large amounts of fructose-sweetened solutions of pure fructose, which A, is not absorbed well, so that fructose feeds endotoxin, which then is, we'll talk about later, is actually a major driver of advanced glycation end products and glycation in general, and oxidative stress and this whole milieu. On top of that, we also just have incredibly high amounts of fructose. We're talking sometimes 50% of the diet or more, which, in nature, you never even if you're eating pure table sugar, you can never have more than 50% of the diet from fructose. And so you get these massive amounts that are basically irrelevant to what any, normal rodent or human would eat. Or you have infusion of fructose where you're getting massive amounts in the blood that are way higher than we would ever get from consuming fructose. And then on top of that, we have some other issues with these animal models and rodents in general with these fructose studies, which is that their capacity for handling fructose is far lower. Their liver's capacity for utilizing and metabolizing fructose is far lower than us as humans. And so they're far more likely to have this buildup of intermediates and increase in fat production and other negative effects there. And they also tend to actually have, as a result of this, much higher levels of fructose in the blood than we do as humans because they don't utilize it as well. So considering all of these factors, these studies looking at high fructose diets in rodents increasing advanced glycation end products really aren't relevant to us as humans consuming any sort of normal food. With all that being said, when it comes to fructose, there really aren't any unique concerns when it comes to fructose and glycation. It's really not a driver here or a culprit here when it comes to glycation and age accumulation and aging and chronic disease states. All right, so we're going to wrap up part 1 here, and in part 2, I'll be going over how glucose and insulin can decrease glycation, why ketogenic diets can be worse than high-carb diets when it comes to advanced glycation end product formation. We'll be going over how autophagy helps to clear ages, but why increasing autophagy is not actually the answer. We'll be talking about the true primary drivers of age accumulation and the best diet and supplements for minimizing glycation. As always, if you enjoyed today's episode, please leave a like or comment wherever you're watching or listening, and also please leave a 5-star rating. All of those things really do a lot to help support the podcast and are very much appreciated. As always, to check out these show notes where you can take a look at the studies, articles, and anything else that I referenced throughout today's episode, you can head over to jfeldmanwellness.com/podcast. And if after listening through the podcast, you're not exactly sure where to get started when it comes to improving your metabolic health, or if you're just looking for some extra guidance on any health issues you might be working on, then head over to jfeldmanwellness.com/call, where you can sign up for a free call with a member of the J. Feldman Wellness team who can provide you with insights and next steps for you to take on your health journey. So again, head over to jfeldmanwellness.com/call to sign up for a free call. And with that, I'll see you on the next one.